The closest star system to our own Sun sits roughly 4.37 light-years away. Alpha Centauri, actually a triple star system with two Sun-like stars orbiting each other and a smaller red dwarf companion, represents humanity's nearest stellar neighbor. That distance of 4.37 light-years translates to about 41.3 trillion kilometers, or if you prefer, roughly 25.7 trillion miles. Light itself, traveling at 299,792 kilometers per second in a vacuum, takes more than 4 years to bridge this gap. This fundamental distance creates the first and most profound challenge for interstellar travel, a barrier so immense that even our fastest spacecraft would require tens of thousands of years to reach Alpha Centauri using current propulsion technology. When we talk about interstellar distances, our usual frames of reference completely fail us. Consider that Voyager 1, launched in 1977 and now the most distant human-made object from Earth, travels at roughly 17 kilometers per second relative to the Sun. At this speed, which represents an impressive achievement for our species, Voyager 1 would need about 73,000 years to reach Alpha Centauri if it were heading in that direction, which it isn't. The probe continues outward into interstellar space, having crossed the heliopause, where the Sun's influence gives way to the interstellar medium, but its journey toward any particular star system remains a matter of cosmic chance rather than intention. The tyranny of the rocket equation governs everything we currently know about spaceflight. Formulated by Konstantin Tsiolkovsky in the late 19th century, this equation describes the relationship between the velocity change a rocket can achieve, the effective exhaust velocity of its propellant, and the ratio between the initial mass of the rocket fully fueled and its final mass after burning all that fuel. The mathematics reveals a harsh truth. To go faster, you need more fuel, but more fuel means more mass, which requires even more fuel to accelerate, creating a vicious cycle that quickly becomes impractical. Chemical rockets, the workhorses of our space program since its inception, burn fuel and oxidizer to produce hot gases that shoot out of a nozzle at high speed. The spacecraft gains momentum in the opposite direction, according to Newton's third law. These rockets have taken us to the moon and sent probes throughout the solar system, but their limitations become glaringly obvious when we consider interstellar distances. The chemical bonds between atoms that store energy in rocket fuel can only release so much energy per unit of mass. This fundamental limitation means that chemical rockets have a maximum exhaust velocity around 4.5 kilometers per second for the best fuel combinations we know. And building a chemical rocket that could reach even a small fraction of light speed would require carrying so much propellant that the numbers become absurd. Calculations show that to accelerate a single kilogram payload to just 1% of light speed using chemical rockets would require more propellant mass than exists in the observable universe. This isn't an engineering challenge waiting for better materials or more efficient designs to solve. The laws of physics themselves make chemical propulsion completely unsuitable for interstellar travel at any reasonable velocity. Ion drives represent a significant improvement over chemical rockets in terms of efficiency. These engines work by accelerating charged particles, typically xenon ions, using electromagnetic fields rather than chemical reactions. The Deep Space One mission, launched in 1998, successfully demonstrated ion propulsion technology, and the Dawn spacecraft used ion engines to explore the asteroid Vesta and the dwarf planet Ceres between 2007 and 2018. Ion engines can achieve exhaust velocities around 30 to 90 kilometers per second, roughly 10 to 20 times better than chemical rockets. The advantage of ion propulsion lies in its efficiency, measured by specific impulse, which indicates how much thrust you get per unit of propellant consumed. While a chemical rocket might have a specific impulse of 450 seconds, ion engines can achieve values exceeding 3,000 seconds. This efficiency means that spacecraft using ion drives can eventually reach higher speeds than chemical rockets while carrying less propellant relative to their payload. However, ion engines produce very little thrust at any given moment. The Dawn spacecraft's Ion engine generated about 90 millinewtons of thrust, roughly equivalent to the weight of a single sheet of paper pressing down on your hand. The combination of high efficiency but low thrust means Ion engines excel at missions within our solar system, where spacecraft can accelerate gradually over months or years. For interstellar travel, though, even Ion propulsion falls woefully short. And to reach Alpha Centauri in a human lifetime using Ion engines would still require either acceleration periods lasting decades or carrying propellant masses that make the mission impractical. Furthermore, Ion engines require electrical power to operate, typically supplied by solar panels in the inner solar system or radioisotope thermoelectric generators for missions to the outer planets. Scaling up Ion propulsion to interstellar velocities would demand power sources far beyond our current capabilities. The speed of light itself imposes an absolute limit that no amount of engineering can circumvent within our current understanding of physics. Einstein's special theory of relativity, published in 1905, fundamentally changed our understanding of space, time, and motion. As objects with mass accelerate toward the speed of light, their energy requirements increase asymptotically. To actually reach light speed would require infinite energy, making it impossible for anything with mass to achieve. Even approaching close to light speed demands enormous energy inputs that grow exponentially as you get closer to that ultimate velocity. Special relativity introduces other complications as well. Time dilation means that as a spacecraft approaches light speed, time passes more slowly for the travelers relative to observers remaining stationary. At 90% of light speed, time aboard the spacecraft would pass at roughly 44% the rate of stationary observers. This effect could actually work in favor of the travelers, since a journey that takes decades by Earth's clocks might feel like only years to those aboard the spacecraft. However, reaching such velocities in the first place remains the fundamental challenge. The energy requirements for relativistic travel become staggering when you work through the numbers. To accelerate a single kilogram of mass to 90% of light speed requires about 1.16 times 10 to the 17th power joules of energy. For context, the entire annual energy consumption of human civilization amounts to roughly 5.8 times 10 to the 20th power joules. And accelerating a modest spacecraft massing perhaps 1,000 kilograms to 90% of light speed would require nearly 2% of humanity's total annual energy output, assuming perfect efficiency in converting whatever energy source we use into kinetic energy of the spacecraft. Nobody seriously proposes achieving perfect efficiency, of course. Real propulsion systems waste energy as heat, electromagnetic radiation, and other forms that don't contribute to accelerating the spacecraft. A more realistic efficiency might be 50% for an advanced system, though most current propulsion methods achieve far less. Doubling the energy requirements means that accelerating our 1,000 kilogram spacecraft now needs 4% of humanity's annual energy budget. These numbers quickly become prohibitive when you consider that we'd also need to carry fuel or reaction mass, dramatically increasing the spacecraft's initial mass and thus the energy needed. Nuclear fission, the process that powers nuclear reactors and atomic weapons, offers energy densities millions of times greater than chemical reactions. When uranium-235 or plutonium-239 nuclei split after absorbing a neutron, they release roughly 200 million electron volts of energy per fission event. This concentration of energy in nuclear reactions compared to chemical bonds fundamentally changes what becomes possible for propulsion, though it doesn't eliminate the challenges of interstellar travel. Project Orion, conceived in the late 1950s at General Atomic, proposed using nuclear explosions to propel a spacecraft. The basic concept involved ejecting nuclear bombs behind the spacecraft at regular intervals, detonating them, and absorbing the explosive force with a massive pusher plate attached to the spacecraft by shock absorbers. Each detonation would deliver an impulse, accelerating the spacecraft forward. The design called for bombs, with yields ranging from small tactical weapons for initial acceleration within the solar system to larger strategic weapons for achieving higher velocities in deep space. The physics of Project Orion actually work. Nuclear weapons release enormous energy very quickly. And then capturing even a small fraction of that energy with a pusher plate could accelerate substantial payloads to impressive velocities. Early studies suggested that an Orion spacecraft could reach Mars in weeks rather than months and could achieve velocities around 3 to 5% of light speed given enough nuclear fuel. At 5% of light speed, the journey to Alpha Centauri would take about 87 years, still longer than a human lifetime, but beginning to approach timeframes that become conceivable for multi-generational voyages or missions with crew in some form of suspended animation. Several factors prevented Project Orion from moving beyond theoretical studies and small-scale testing with conventional explosives. The Partial Nuclear Test Ban Treaty of 1963 prohibited nuclear explosions in the atmosphere, underwater, and in space, effectively ending any near-term possibility of testing or deploying an Orion-style spacecraft. Beyond political and treaty considerations, the engineering challenges were immense. Designing a pusher plate that could withstand thousands of nuclear detonations, each releasing temperatures hotter than the surface of the Sun, pushed the limits of materials science. The shock absorbers connecting the pusher plate to the rest of the spacecraft needed to smooth out the violent impulses while still efficiently transferring momentum. Environmental and ethical concerns also played a role. Launching an Orion spacecraft from Earth's surface would have exposed the planet to radioactive fallout from the nuclear pulses used during ascent. Later designs proposed assembling Orion spacecraft in orbit and igniting the nuclear pulse system only after reaching safe distances from Earth. But this added complexity and cost. The sheer number of nuclear weapons required for an interstellar Orion mission numbered in the hundreds of thousands or millions, depending on the desired velocity and mission profile. Manufacturing, transporting, and managing such an arsenal presented logistical and security challenges on an unprecedented scale. Despite these obstacles, Orion represented the first serious proposal for interstellar propulsion that relied on known physics and available technology, even if that technology would need significant refinement. Freeman Dyson, the physicist and mathematician who worked on the Orion project, later wrote extensively about its potential for opening up the solar system and beyond to human exploration. His calculations suggested that a well-designed Orion spacecraft could transport thousands of tons of payload between planets or to the stars, effectively serving as a space-going city rather than a cramped capsule. Nuclear thermal rockets represent a less explosive approach to harnessing nuclear energy for propulsion. Instead of detonating bombs, these engines use a nuclear reactor to heat propellant, typically liquid hydrogen, to extremely high temperatures before expelling it through a nozzle. The nuclear reactor replaces the combustion chamber of a chemical rocket, but the basic principle of heating and expanding a working fluid to generate thrust remains the same. The advantage comes from the much higher temperatures achievable with nuclear reactions compared to chemical combustion. The NERVA program, which stood for Nuclear Engine for Rocket Vehicle Application, ran from 1961 to 1973 in the United States. Engineers built and tested several nuclear rocket engines, successfully demonstrating that the concept worked. These engines achieved exhaust velocities around 8 to 9 kilometers per second, roughly double that of the best chemical rockets, and specific impulses approaching 850 seconds. And the program proved the technical viability of nuclear thermal propulsion, but was cancelled as part of broader cuts to the space program following the Apollo moon landings. For missions within the solar system, nuclear thermal rockets offer significant advantages over chemical propulsion. The higher exhaust velocity translates to faster trip times or greater payload capacity for the same amount of propellant. A nuclear thermal rocket could reach Mars in half the time of a chemical rocket, reducing crew exposure to cosmic radiation during the interplanetary coast and cutting life support requirements. However, for interstellar distances, even nuclear thermal propulsion doesn't provide the performance needed. And the fundamental limitation of nuclear thermal rockets stems from the same issue that constrains chemical rockets: They must carry and heat a physical propellant. The reactor's maximum operating temperature limits how fast propellant can be expelled, and materials constraints keep these temperatures well below what would be ideal. Tungsten, one of the highest melting point materials available, melts at 3,422 degrees Celsius. Reactor designs must keep structural components below their melting points while maximizing the temperature of the propellant flowing through the reactor core. This thermal management challenge limits performance improvements beyond the approximately two-fold advantage over chemical propulsion that Nerva demonstrated. And advanced concepts for nuclear thermal propulsion include gas core reactors, where the nuclear fuel itself is in a gaseous or plasma state, separated from the propellant by electromagnetic fields or clever fluid dynamics. This approach could potentially achieve exhaust velocities around 30 km per second by allowing much higher operating temperatures, since solid reactor components no longer need to remain in direct contact with the nuclear reaction. However, gas core nuclear rockets remain theoretical, with enormous engineering challenges in containing and controlling a nuclear plasma while efficiently transferring its energy to propellant. Nuclear electric propulsion combines nuclear reactors with electric propulsion systems like ion engines. The reactor generates electricity that powers the ion drive, eliminating the need for solar panels and providing consistent power far from the sun, where solar panels become ineffective. This approach could enable faster missions to the outer solar system and potentially to the Oort cloud, the vast shell of icy objects surrounding our solar system at distances up to 100,000 astronomical units from the sun. For perspective, Pluto orbits at about 40 astronomical units at its most distant, so the Oort cloud represents the frontier where the sun's gravitational influence begins to give way to the gravitational influence of neighboring stars. The problem with nuclear electric propulsion for interstellar travel again comes down to the fundamental limitation of all reaction drives. They must carry reaction mass and expel it to generate thrust. And even with a nuclear reactor providing abundant power and ion engines achieving excellent efficiency, accelerating a spacecraft to relativistic velocities would require carrying more reaction mass than practically possible. The rocket equation still governs the relationship between velocity change, exhaust velocity, and mass ratio, and even with the improved performance of ion propulsion, reaching significant fractions of light speed requires mass ratios that grow exponentially. Fusion reactions, which power the Sun and other stars, offer energy densities even greater than fission. When light atomic nuclei like hydrogen isotopes combine to form heavier elements, they release energy according to Einstein's famous equation relating mass and energy. The mass of the resulting nucleus is slightly less than the combined mass of the reactants, and this missing mass converts to energy. Fusion reactions release roughly 4 times more energy per unit mass than fission reactions, and the fuel is far more abundant, with deuterium readily extractable from seawater. The challenge with fusion power lies in achieving and maintaining the conditions necessary for fusion reactions to occur. Nuclei are positively charged and repel each other electromagnetically. Overcoming this electrostatic repulsion requires either extreme temperatures on the order of tens of millions of degrees or confinement times long enough for quantum tunneling to allow nuclei to fuse despite their mutual repulsion. Stars accomplish fusion through sheer gravitational pressure. But we lack that option on Earth or aboard spacecraft. Magnetic confinement fusion uses powerful magnetic fields to contain a plasma of fusion fuel at temperatures exceeding 100 million degrees Celsius. The ITER project, currently under construction in France, represents the largest magnetic confinement experiment ever attempted and aims to demonstrate sustained fusion reactions that produce more energy than required to maintain them. Tokamak reactors, the design ITER uses, confine plasma in a toroidal shape using complex magnetic field geometries. Other approaches include stellarators, which use twisted magnetic coils to achieve confinement without requiring electrical currents through the plasma itself. Inertial confinement fusion takes a different approach. or using laser beams or particle beams to compress and heat tiny pellets of fusion fuel so rapidly that fusion occurs before the fuel can fly apart. The National Ignition Facility in California demonstrated fusion ignition in 2022, achieving a reaction that produced more fusion energy than the laser energy delivered to the fuel pellet. This milestone marked a significant achievement, though the total energy consumed by the facility to power the lasers far exceeded the fusion energy released, and practical power generation using inertial confinement faces substantial obstacles. For spacecraft propulsion, fusion offers tantalizing possibilities. A fusion rocket could theoretically achieve exhaust velocities of several % of light speed by directing the fusion reaction products through a magnetic nozzle. The energy released per unit of fuel mass far exceeds any chemical or fission process, potentially enabling missions to nearby stars within decades rather than millennia. Various conceptual designs exist, from magnetic confinement engines similar to tokamaks to inertial confinement systems using laser or particle beam compression of fuel pellets injected into a reaction chamber. The Daedalus study, conducted by the British Interplanetary Society from 1973 to 1978, designed a theoretical fusion-powered spacecraft capable of reaching nearby stars. The design called for a two-stage vehicle using inertial confinement fusion, with electron beams compressing and igniting deuterium and helium-3 fuel pellets at a rate of 250 per second. As the fusion reactions would occur in a reaction chamber surrounded by magnetic fields that channeled the reaction products rearward, generating thrust. Calculations suggested Daedalus could reach 12% of light speed, allowing it to reach Barnard's star, about 6 light-years distant, in roughly 50 years. Project Icarus, a successor to Daedalus undertaken from 2009 to 2014, revisited and updated the fusion spacecraft design using advances in physics and engineering from the intervening decades. While Icarus refined various aspects of the concept, it confirmed the basic feasibility of fusion propulsion for interstellar missions, at least from a theoretical standpoint. Both studies acknowledged that actually building such a spacecraft requires first solving the fundamental challenge of controlled fusion power. That's something we haven't yet achieved despite decades of research and billions of dollars invested. The most significant obstacle to fusion propulsion stems from our inability to achieve practical fusion power generation here on Earth under laboratory conditions. If we can't build a fusion reactor that produces more useful energy than it consumes while operating on the ground with unlimited mass and volume budgets and teams of engineers maintaining it, building a fusion reactor compact and reliable enough to operate autonomously for decades in deep space seems hopelessly optimistic. Progress continues, and recent breakthroughs suggest fusion power generation may become viable in the coming decades, but translating stationary fusion reactors into working spacecraft engines adds layers of complexity. Fusion rocket designs must balance the plasma confinement time and pressure required for fusion with the need to direct reaction products efficiently through an exhaust to generate thrust. In a power-generating fusion reactor, you want to contain the plasma as long as possible to maximize energy extraction. In a fusion rocket, you need some confinement to achieve fusion, but you also want to channel the reaction products rearward quickly to produce thrust. This tension between confinement for fusion and directed exhaust for propulsion complicates the engineering substantially. Another consideration involves the fusion fuel itself. The easiest fusion reaction to achieve, requiring the lowest temperature and pressure, combines deuterium and tritium. Unfortunately, tritium is radioactive with a half-life of about 12 years, meaning it decays relatively quickly and must be produced artificially through neutron bombardment of lithium. A spacecraft using deuterium-tritium fusion would need to either carry its tritium from Earth, accepting that a significant fraction would decay during a multi-decade journey, or manufacture tritium en route, adding complexity and mass. Alternative fusion reactions, such as deuterium-deuterium or deuterium-helium-3, avoid the tritium problem, but require higher temperatures and pressures to achieve comparable reaction rates. Deuterium occurs naturally as about 0.015% of hydrogen atoms and can be extracted from water, making it effectively unlimited for any conceivable number of spacecraft. Helium-3, however, is extremely rare on Earth. With most existing stocks consisting of a few hundred kilograms accumulated from nuclear weapons' tritium decay. The Moon's surface contains helium-3 deposited by the solar wind over billions of years, but extracting and refining it would require an established lunar industrial base, putting this fuel source far into the future. The engineering realities of containment materials present another hurdle. Fusion reactions produce not only energy but also high-energy neutrons and other radiation that bombard the reactor's walls. Over time, this neutron bombardment damages materials, making them brittle and eventually unusable. Power-generating fusion reactors on Earth would need periodic replacement of these first-wall materials, but a fusion rocket on an interstellar journey can't pull into a service station for maintenance. Materials that can withstand decades of continuous neutron bombardment while maintaining structural integrity remain an active area of research. Despite these challenges, fusion propulsion represents perhaps the most promising approach to interstellar travel using reasonably understood physics. Unlike concepts requiring exotic physics or materials that may not exist, fusion reactions definitively occur, as evidenced by every star in the sky and by nuclear weapons tests. We know fusion works. We know the energy released by various fusion reactions. The engineering challenges, while immense, seem potentially solvable given sufficient time, resources, and motivation. This stands in contrast to more speculative propulsion concepts that depend on physics we haven't confirmed experimentally. Speaking of more speculative concepts, an antimatter represents the ultimate in energy density. When matter and antimatter meet, they annihilate completely, converting their entire mass to energy according to Einstein's equation. This complete mass-to-energy conversion means antimatter carries about 2 orders of magnitude more energy per unit mass than fusion reactions. Even tiny amounts of antimatter contain extraordinary energy. A single gram of antimatter annihilating with a gram of matter would release about 180 terajoules, equivalent to the Hiroshima atomic bomb. The potential of antimatter for spacecraft propulsion becomes clear when you consider these energy densities. An antimatter rocket could theoretically achieve exhaust velocities approaching the speed of light itself, since the annihilation products initially move at relativistic speeds. Efficiently capturing and directing this energy presents engineering challenges, but the fundamental energy budget for relativistic spaceflight becomes much more favorable when using antimatter fuel. Unfortunately, antimatter faces practical obstacles that currently put it firmly in the realm of science fiction rather than near-term engineering proposals. Antimatter doesn't occur naturally in our region of space. The universe around us consists almost entirely of normal matter, with antimatter appearing only occasionally as a product of high-energy particle interactions. To obtain antimatter for rocket fuel, we must create it in particle accelerators by colliding particles at high energies and capturing the antimatter particles produced. Current antimatter production capabilities amount to tiny fractions of a gram per year worldwide, with costs estimated at trillions of dollars per gram. The European Organization for Nuclear Research operates antimatter production facilities that generate antiprotons at rates measured in nanograms per year. These production rates reflect fundamental physical limitations rather than merely technological shortcomings. Every antiproton created requires immense energy input, and the efficiency of converting energy into antimatter remains extremely low. The energy needed to produce antimatter far exceeds the energy that same antimatter could later release in an annihilation reaction. Storage presents another formidable challenge. Antimatter cannot touch any normal matter without instantly annihilating, so containment systems must hold antimatter particles suspended in electromagnetic fields within a perfect vacuum. And the Alpha experiment at CERN successfully trapped anti-hydrogen atoms for periods exceeding 16 minutes, a remarkable achievement that nonetheless falls astronomically short of what a spacecraft would require. An interstellar mission might last decades or centuries, demanding antimatter storage systems that maintain perfect containment through acceleration, deceleration, and the harsh radiation environment of deep space. Current antimatter traps consist of superconducting magnets that create magnetic bottles, regions where charged particles spiral along magnetic field lines without touching physical walls. These systems consume significant power to maintain the magnetic fields and the cryogenic temperatures needed for superconductivity. A spacecraft carrying antimatter would need redundant containment systems, or backup power supplies, and fail-safe mechanisms to prevent catastrophic annihilation events. The mass of these containment systems would constitute a substantial fraction of the spacecraft's total mass, reducing the net performance advantage that antimatter fuel might otherwise provide. Even assuming we could produce and store sufficient antimatter, the propulsion system itself poses engineering challenges unlike anything we've constructed. An antimatter rocket would direct the energy from matter-antimatter annihilation into a thrust-producing mechanism. One approach involves allowing antiprotons to annihilate with protons in a target, generating charged pions that could be directed by magnetic fields to produce thrust. The pions decay quickly into muons and neutrinos, but the muons could contribute to thrust if directed properly. And this direct thrust approach offers high efficiency but requires precise control over particle interactions occurring at relativistic speeds. Alternative designs propose using antimatter annihilation energy to heat a propellant, much like nuclear thermal rockets, but with far higher energy densities. The heated propellant would expand through a nozzle, producing thrust through conventional rocket principles. This approach sacrifices some efficiency compared to direct annihilation thrust, but simplifies engineering by separating the annihilation chamber from the nozzle. The propellant could be ordinary matter, perhaps liquid hydrogen, which would absorb energy from the annihilation products and reach temperatures far exceeding what any nuclear reactor could achieve. Theoretical studies suggest that antimatter rockets might achieve exhaust velocities approaching significant fractions of light speed, potentially reaching 10% the speed of light or more. Such performance would place Alpha Centauri within reach on timescales of several decades rather than millennia. However, the quantity of antimatter required scales with mission parameters in ways that quickly overwhelm production capabilities. A spacecraft massing just a few tons might require kilograms or even tons of antimatter, quantities that exceed cumulative human antimatter production by factors of billions. The energy equivalence equation governs antimatter annihilation, converting mass directly into energy with 100% efficiency. At 1 kilogram of antimatter, annihilating with 1 kilogram of matter releases energy equivalent to approximately 43 megatons of TNT, comparable to the largest nuclear weapons ever tested. This tremendous energy density makes antimatter the ultimate rocket fuel from a theoretical standpoint, yet also underscores the dangers inherent in handling such materials. Any containment failure would release catastrophic amounts of energy instantaneously, making antimatter rockets potentially hazardous to spacecraft crews and anything nearby during fueling operations. Particle beam propulsion offers a different approach to achieving high velocities without carrying propellant. In these schemes, a powerful laser or particle accelerator stationed in the solar system would direct a beam of energy or particles toward a spacecraft, which would capture this energy using a sail or magnetic field and convert it into velocity. The spacecraft would carry no fuel, relying entirely on the beam for acceleration. This architecture transfers the energy production problem away from the spacecraft itself, allowing the accelerating installation to be arbitrarily large and powerful since it doesn't need to move. Laser-pushed light sails represent the simplest implementation of beam propulsion. A spacecraft equipped with an enormous, ultra-thin reflective sail would be accelerated by photons from a massive laser array. The momentum transfer from reflected photons would gradually push the spacecraft to high velocities. The Breakthrough Starshot initiative proposes exactly such a system. It's envisioning gram-scale spacecraft accelerated to 20% light speed by a ground-based laser array delivering gigawatts of power. At such velocities, these tiny probes could reach Alpha Centauri in approximately 20 years, though they would carry minimal instrumentation and offer no possibility of deceleration at their destination. Scaling light sail concepts to larger spacecraft encounters the familiar problem of diminishing returns. The sail area must increase faster than spacecraft mass to maintain acceleration, but larger sails accumulate mass themselves and become increasingly difficult to manufacture as perfectly flat, reflective surfaces. Any imperfections in sail shape or reflectivity create unbalanced forces that could cause the spacecraft to tumble or veer off course. The sail must also withstand intense laser heating without degrading, requiring exotic materials that remain highly reflective while absorbing minimal energy. Deceleration poses another challenge for laser-pushed light sails. A spacecraft accelerated to 20% light speed cannot slow down using the same laser that pushed it, since the laser remains behind in the solar system. One proposed solution involves detaching a portion of the sail at the mission midpoint, allowing the laser to illuminate this separated section, which would then reflect light back toward the main spacecraft to decelerate it. The geometry and timing required for such maneuvers approach the limits of practical feasibility, requiring extreme precision across distances of light years. But magnetic sails offer an alternative for both acceleration and deceleration. A spacecraft deploying a loop of superconducting cable carrying enormous current would generate a magnetic field spanning hundreds or thousands of kilometers. This field could reflect charged particles from a particle beam for acceleration or interact with the tenuous interstellar medium for deceleration. The advantage of magnetic sails lies in their ability to create large effective collection areas without requiring vast physical structures. The magnetic field itself does the work of capturing momentum from incoming particles or from the interstellar medium. The Bussard ramjet concept, proposed in the 1960s, envisions a spacecraft using a magnetic field to collect hydrogen from the interstellar medium itself, thus then fusing this hydrogen for propulsion. The spacecraft would scoop up protons from space using its magnetic field, compress them to fusion conditions, and exhaust the fusion products to produce thrust. This approach theoretically eliminates the need to carry fuel, allowing unlimited acceleration limited only by the fusion reactor's efficiency and the density of interstellar hydrogen. A Bussard ramjet could theoretically accelerate continuously for years, reaching velocities approaching light speed given sufficient time. Practical examination of the ramjet concept reveals severe limitations. The interstellar medium contains roughly 1 hydrogen atom per cubic centimeter, a density so low that collecting sufficient fuel requires magnetic collection fields spanning thousands of kilometers. Thus, the mass of superconducting cables and power systems needed to generate such fields would be substantial. Furthermore, the spacecraft would encounter drag from interacting with the interstellar medium, and at some velocity, this drag would exceed the thrust produced from fusing collected hydrogen. Detailed calculations suggest that pure Bussard ramjets cannot achieve the extreme velocities originally envisioned, though hybrid designs combining ramjet collection with onboard fuel might offer better performance. The physics of interstellar travel ultimately derives from the rocket equation and the energy requirements for accelerating mass. Every propulsion system must either carry its energy source and propellant, receive energy from external sources, or extract energy and reaction mass from the environment. Chemical rockets carry both fuel and oxidizer. Nuclear rockets carry fuel and use propellant. Antimatter rockets would theoretically carry the ultimate fuel, and beam-propelled spacecraft receive energy externally. Bussard ramjets would gather fuel from space itself. Each approach faces distinct limitations, and none offers an obviously practical path to crewed interstellar missions within current or near-future technology. Beyond these comparatively conventional approaches, speculative propulsion concepts push into territory where physics becomes uncertain or requires capabilities far beyond current technology. Warp drives, inspired by Einstein's general relativity, propose manipulating space-time itself to achieve faster-than-light travel without violating relativity's local speed limit. The Alcubierre drive, Named after physicist Miguel Alcubierre, describes a space-time configuration where space contracts ahead of a spacecraft and expands behind it, allowing the spacecraft to ride a bubble of normal space, while the bubble itself moves faster than light relative to surrounding space. The mathematical framework of general relativity permits such space-time geometries, but creating them would require exotic matter with negative energy density, something never observed in nature and possibly forbidden by quantum field theory. Even if exotic matter exists and could be produced in macroscopic quantities, the energy requirements for generating an Alcubierre warp bubble appear to be immense, possibly exceeding the total mass energy of observable galaxies. More recent refinements of the concept have reduced these energy requirements somewhat, but they remain far beyond anything achievable with known physics and engineering. Wormholes represent another space-time structure permitted by general relativity, potentially connecting distant regions of space through a tunnel-like shortcut. If traversable wormholes could be created and stabilized, they might allow near-instantaneous travel across interstellar or even intergalactic distances. However, like warp drives, wormholes require exotic matter to remain open and traversable. The energy conditions needed to prevent wormholes from collapsing violate known physics, making their existence highly speculative. Even if natural wormholes exist somewhere in the universe, we have no method for detecting them, or more importantly, for creating them where needed for interstellar travel. These speculative concepts often appear in science fiction because they solve the fundamental problem of interstellar travel by circumventing rather than accepting the limitations imposed by physics. Warp drives and wormholes make interesting thought experiments that test our understanding of general relativity's implications, but they remain firmly in the realm of speculation rather than practical engineering. No experimental evidence supports the existence of exotic matter, and theoretical work increasingly suggests that quantum field theory may forbid the kinds of negative energy densities these concepts require. The quantum vacuum, once thought to be truly empty space, actually seethes with virtual particles constantly appearing and annihilating. These quantum fluctuations have measurable effects, producing forces like the Casimir effect, where two uncharged metal plates placed very close together experience an attractive force due to differences in quantum vacuum fluctuations between the plates and outside them. Some speculative propulsion concepts propose harnessing vacuum energy, either through Casimir effect mechanisms or by other means of extracting energy from the quantum vacuum. The practical challenges of vacuum energy propulsion remain formidable. The Casimir force is extraordinarily weak, requiring plate separations of nanometers to produce measurable effects. Scaling such forces to useful propulsion levels would require enormous surface areas of precisely positioned plates, and the total energy extractable from vacuum fluctuations remains unclear. Thermodynamic arguments suggest that true perpetual motion remains impossible, so vacuum energy propulsion would ultimately be limited by conservation of energy and entropy considerations. These concepts remain interesting areas for theoretical investigation, but offer no clear path to practical propulsion systems. Some researchers have explored whether momentum could be exchanged with the quantum vacuum itself, producing thrust without expelling propellant. The controversial M drive claimed to achieve this through electromagnetic resonance in a tapered cavity, but subsequent careful experiments failed to replicate the original results or demonstrated that apparent thrust came from thermal effects or other experimental artifacts. The consensus among physicists holds that conservation of momentum remains inviolable, and any propulsion system must either expel reaction mass or interact with external fields or particles. Systems claiming to violate momentum conservation generally fail upon careful examination. Returning to approaches grounded in established physics, improvements in existing propulsion technologies could gradually extend our reach toward nearby stars. Electric propulsion systems continue to improve, and with Hall effect thrusters and ion drives achieving higher thrust levels and longer operational lifetimes. These incremental advances make robotic missions to the outer solar system increasingly practical, and each improvement in efficiency or power reduces travel times. However, the fundamental limitations of exhaust velocity and power availability still constrain electric propulsion to applications within the solar system for the foreseeable future. Advanced nuclear propulsion concepts beyond Orion and conventional nuclear thermal rockets include nuclear electric propulsion, where a nuclear reactor generates electricity to power electric thrusters. This approach combines the long operational lifetime and high energy density of nuclear reactors with the high exhaust velocity of electric propulsion. The reactor can operate continuously for years, providing steady thrust that gradually builds up velocity. The main limitation remains power, as reactor mass scales with power output, and higher thrust requires more power, which requires more reactor mass. The Kilopower project, developed for Mars surface power applications, demonstrates one approach to compact nuclear reactors suitable for spacecraft. Thus, these small reactors use heat pipes to transfer thermal energy from a uranium core to Stirling engines that convert heat into electricity. Scaled-up versions might provide sufficient power for electric propulsion systems on deep space missions. However, even optimistic projections suggest that nuclear electric propulsion remains best suited for missions within the solar system, or perhaps to its immediate surroundings, rather than true interstellar distances. Fusion propulsion continues to attract research interest because fusion offers high energy density without the radioactive fuel handling challenges of fission reactors. Various fusion approaches have been proposed for spacecraft, including magnetic confinement similar to tokamak reactors, inertial confinement using lasers or particle beams, and more exotic schemes involving antimatter catalyzed fusion or muon catalyzed fusion. Each approach attempts to achieve the conditions necessary for fusion: extremely high temperatures and pressures or densities within a system compact and light enough for spacecraft use. The challenge of achieving net energy gain from fusion has proven difficult even in massive laboratory installations consuming enormous amounts of power. Recent experiments at the National Ignition Facility achieved fusion ignition, where fusion reactions produced more energy than the laser energy delivered to the fuel pellet, but the overall system efficiency remains extremely low. The laser system consumes hundreds of times more energy than the fusion reactions produce. For spacecraft propulsion, fusion reactors would need to achieve much higher efficiency, operate continuously rather than in pulses, and weigh a small fraction of the spacecraft total mass. Direct fusion drive concepts propose using the fusion reaction products, primarily high-energy charged particles, directly for thrust rather than converting fusion energy to electricity or using it to heat propellant. This approach maximizes efficiency by eliminating energy conversion steps and allowing fusion products to escape directly from the reactor to produce thrust. The Princeton Satellite Systems Direct Fusion Drive envisions a compact fusion reactor using a particular magnetic field configuration to contain fusion plasma, while allowing some fusion products to escape in a directed beam for propulsion. Theoretical performance estimates suggest exhaust velocities up to hundreds of kilometers per second, orders of magnitude better than chemical rockets, but still far below what true interstellar missions would require. Antimatter catalyzed fusion attempts to trigger fusion reactions using small quantities of antimatter rather than relying on conventional heating and compression. When antiprotons contact protons, the annihilation releases enormous energy in a tiny volume, potentially creating conditions where surrounding fusion fuel can react. This approach would drastically reduce the antimatter requirements compared to pure antimatter rockets, since the antimatter merely initiates reactions rather than providing all the energy. Theoretical studies suggest that grams of antimatter might catalyze fusion of tons of fusion fuel, making the antimatter requirements at least theoretically achievable with enhanced production facilities. Research into antimatter-catalyzed fusion faces dual challenges of antimatter production and controlled fusion ignition. The concept requires precisely timed injection of tiny amounts of antimatter into fusion fuel, with the annihilation occurring at exactly the right location and moment to trigger a fusion burn. The engineering complexity rivals that of inertial confinement fusion, but adds the complication of antimatter handling. No experimental demonstration of antimatter-catalyzed fusion has occurred, leaving the concept in the realm of theoretical possibility rather than demonstrated technology. The vast gulf between our current technological capabilities and what interstellar missions require manifests in multiple dimensions simultaneously. Energy storage and generation systems fall short by orders of magnitude. Propulsion efficiency and exhaust velocity lag far behind requirements. Spacecraft longevity and reliability would need to exceed anything achieved in space exploration history. Even our fastest spacecraft would require tens of thousands of years to reach Alpha Centauri, and technologies capable of reducing this to decades or centuries remain theoretical at best. A thought experiment illustrates the scale of the challenge. Imagine Earth decided to mount an interstellar mission using the most advanced propulsion technology reasonably foreseeable in the next several decades. This mission would likely employ nuclear-electric propulsion, perhaps with a modest fusion reactor, if fusion power becomes practical. The spacecraft would accelerate continuously for years, building velocity gradually, then coast for decades before beginning deceleration. Total mission duration might span a century, requiring robust autonomous systems capable of operating without human intervention across interstellar distances. Such a mission would carry scientific instruments to study the Alpha Centauri system, perhaps including cameras, spectrometers, magnetometers, and particle detectors. Communication with Earth would involve powerful radio transmitters and large antenna arrays, since even laser communication becomes challenging across 4 light-years. The data rate would be slow, possibly kilobits per second at best, and each message would take years to reach Earth. The spacecraft itself would need to weigh several tons to carry all necessary equipment, requiring propulsion systems capable of accelerating this mass to velocities approaching a significant fraction of light speed. Running calculations for this hypothetical mission reveals daunting numbers. Accelerating a 5-ton spacecraft to 10% light speed requires kinetic energy of roughly 4 times 10 to the 18th joules, equivalent to about 100 megatons of TNT, or the energy consumption of all human civilization for several hours. And if the propulsion system achieves 50% efficiency in converting fuel energy to kinetic energy, double that amount of fuel energy would be needed. For fusion propulsion, this translates to fusing roughly 100 kilograms of hydrogen, assuming deuterium-tritium fusion and perfect conversion of mass deficit to kinetic energy. The reactor and propulsion system needed to achieve this performance would themselves mass several tons, meaning the initial spacecraft mass would actually be perhaps 10 tons rather than 5. The scaling quickly becomes unfavorable, with fuel requirements increasing to maintain performance as the spacecraft grows heavier. The mission might ultimately require dozens of tons to be launched from Earth and assembled in space. Pushing the boundaries of heavy lift launch capability, even with future improvements in launch technology. Deceleration presents equal challenges. Without a means to slow down, the spacecraft would flash through the Alpha Centauri system in days or hours, barely enough time to gather scientific data. Deceleration requires either carrying additional fuel mass equal to the acceleration fuel, doubling the mission mass, or employing alternative deceleration methods like magnetic sails interacting with the interstellar medium or particle beams sent from Earth. Each option introduces additional complexity and mass, further reducing the mission's overall feasibility. The time commitment for such a mission spans generations. Even at optimistic velocities of 10% light speed, the journey would take 40 years each way, plus deceleration time, with an additional 4 years for radio signals to return to Earth. Scientists and engineers working on mission launch would not live to see the results. This multi-generational timescale requires long-term commitment and funding stability, unlike anything space programs have previously achieved. The political and social challenges may exceed the technical obstacles. Human-crewed missions multiply all these challenges several-fold. Life support systems must sustain crew members for decades, recycling air, water, and then food with near-perfect efficiency. The spacecraft must provide radiation shielding against cosmic rays and solar particle events, adding mass. Psychological factors of isolation and confinement demand attention, perhaps requiring rotating habitats to provide artificial gravity and prevent muscle and bone loss. Medical facilities must handle any health problems that arise during the voyage without possibility of resupply from Earth. The human factor introduces irreducible minimums in spacecraft size and mass. People require space to live, supplies to consume, and systems to maintain health. Even the most efficient spacecraft designed for human passengers would mass hundreds of tons at minimum, pushing propulsion requirements far beyond robotic missions. As the fuel needed to accelerate and decelerate such massive vessels approaches science fiction levels, requiring propulsion technologies several steps beyond our current capabilities. One proposed solution to the human lifetime problem involves generation ships, vessels large enough to support populations across multiple generations. Children born aboard would continue the mission started by their great-grandparents, eventually reaching the destination star system centuries after launch. Generation ships would be cities in space, requiring closed ecological systems, sustainable food production, and social structures capable of maintaining mission purpose across lifetimes. The engineering challenges of creating stable, enclosed ecological systems that can sustain themselves indefinitely remain unsolved even for small-scale experiments on Earth. Suspended animation or hibernation offers a theoretical alternative to generation ships, placing crew members in metabolically reduced states for the journey duration. Various approaches have been proposed, from chemical-induced hibernation similar to what bears experience, to more extreme concepts involving cryogenic preservation. Medical research has achieved some success with therapeutic hypothermia for trauma patients and suspended animation for hours or days, but extending these techniques to years or decades introduces unknowable biological challenges. The risk of systems failure killing hibernating crew members would be unacceptable without extensive testing, impossible to perform on Earth. And some futurists propose using advanced robotics and artificial intelligence to replace human crews entirely, sending machine explorers to the stars instead. Robotic missions eliminate life support requirements and avoid ethical concerns about human lives at risk, but they introduce their own challenges around autonomous decision-making, repair capabilities, and communication latency. A robot explorer at Alpha Centauri could not consult with Earth-based controllers in real time, requiring sophisticated AI to handle unexpected situations. Current AI capabilities fall well short of what such missions would require, though rapid progress in machine learning suggests this gap might narrow in coming decades. The destination choice itself profoundly affects mission feasibility. Alpha Centauri represents the nearest star system, making it the obvious first target for interstellar exploration, but other nearby stars might offer advantages. Barnard's star, roughly 6 light-years distant, is a single red dwarf rather than a binary system, potentially simplifying orbital mechanics around it. Tau Ceti, 12 light-years away, is similar to our Sun and known to host multiple planets, making it scientifically interesting despite the greater distance. Each of these targets requires decades to reach even at substantial fractions of light speed, and no compelling advantage makes one obviously superior to others. The distribution of stars in our galactic neighborhood reveals that truly nearby stars remain sparse. Within 10 light-years of Earth, only 14 star systems exist, most of them dim red dwarfs. Within 20 light-years, the number increases to about 100 stellar systems, but distance increases linearly, while travel time increases faster than linearly for most propulsion systems. The nearest star-forming regions, young stellar clusters, or exotic objects like neutron stars lie hundreds or thousands of light-years away, completely beyond reach of any conceivable propulsion technology for the foreseeable future. This sparsity of nearby stars means that early interstellar missions would target whatever happens to lie closest, rather than choosing destinations based on particular scientific interest or potential for harboring life. We would explore Alpha Centauri because it's there and nearest, not because it offers compelling advantages over other systems. The recently discovered planets around Proxima Centauri are one of the Alpha Centauri system's components, add some scientific motivation, but the fundamental driver remains proximity rather than particular features of the destination. The reality that proximity drives target selection reveals a deeper issue about the current state of interstellar propulsion. We are constrained not just by the speed we can achieve, but by our inability to choose among destinations. A civilization with truly capable interstellar technology would survey multiple systems, select the most promising targets based on scientific criteria, and route missions accordingly. Instead, we're limited to discussing whichever stars happen to fall within a narrow bubble around our solar system, treating distance as the overwhelming consideration that drowns out all other factors. And this constraint becomes even more apparent when considering the broader galactic neighborhood. Within 50 light-years of Earth, hundreds of star systems exist, many with confirmed exoplanets. Some of these planets orbit within their star's habitable zone, where liquid water might exist on rocky surfaces. Others orbit red dwarf stars that could remain stable for trillions of years, offering timescales for biological evolution that dwarf anything possible around our Sun. Yet all these potentially fascinating destinations remain equally inaccessible under current propulsion concepts. The difference between a 10,000-year journey and a 20,000-year journey lacks practical significance when both timescales exceed the entire span of recorded human history. And the generation ship concept attempts to address these timescales by accepting them rather than fighting against them. Instead of trying to reach other stars within human lifetimes, generation ships would carry populations that live, reproduce, and die during the journey, with descendants eventually reaching the destination. This approach sidesteps the propulsion problem by treating the spacecraft as a traveling world rather than a vehicle. Instead of asking how to go faster, it asks how to sustain a human community across centuries or millennia. Yet generation ships introduce their own formidable technical challenges. The vessel would need to recycle air, water, and nutrients with near-perfect efficiency for hundreds of generations. Even small losses accumulating over centuries would eventually deplete essential resources. And the ship would require robust agricultural systems to provide food, along with industrial facilities to manufacture replacement parts and maintain infrastructure. The closed ecosystem would need to remain balanced, avoiding population collapses or resource exhaustion. These requirements demand a level of environmental engineering far beyond anything humanity has demonstrated, even in brief experiments like Biosphere 2, which struggled to maintain balance over just a few years. The social and psychological aspects of generation ships present equally daunting challenges. The crew would need to maintain cultural continuity across dozens of generations, preserving the knowledge and motivation necessary to complete a mission whose goal the original travelers would never see. The population would need to remain genetically viable despite limited numbers, avoiding inbreeding depression while preventing population growth from overwhelming the ship's carrying capacity. Governance systems would need to function across centuries without the stabilizing feedback that planetary civilizations receive from their environment. The psychological effects of growing up, knowing you'll spend your entire life inside a closed vessel, unable to ever step outside or experience a planetary surface, remain unknown but potentially severe. Some theorists have proposed solutions like hibernation or suspended animation, allowing the crew to sleep through most of the journey and wake only near arrival. This would eliminate many generation ship problems while still allowing human beings to make the journey. However, the technology for reliably suspending and reviving human metabolism over centuries doesn't exist. Medical science can induce hypothermia for hours or perhaps days, but maintaining a human body in stasis for decades or centuries while preventing cellular damage, particularly to the brain, remains purely speculative. Even if such technology were developed, the ship would still need to function autonomously for the entire journey, maintaining life support systems for dormant passengers and repairing itself without human intervention. The question of what happens when a generation ship or sleeper ship arrives introduces yet another layer of complexity. The destination system would be largely unknown despite whatever observations we could make from Earth. Radio signals carrying detailed survey data back from Alpha Centauri would take over 4 years to reach Earth, meaning any course corrections or mission planning based on that data would face similar delays. The crew would need to arrive prepared for a wide range of scenarios, carrying equipment and supplies for planetary colonization, asteroid mining, or space habitat construction depending on what they find. If the destination system contains a habitable planet, the challenges shift to planetary colonization, which itself involves formidable obstacles. The planet's biochemistry might be incompatible with human life, even if liquid water and breathable atmosphere exist. Native microorganisms might be harmless, helpful, or deadly to human biology. The colonists would need to establish agriculture, industry, and infrastructure while potentially wearing life support equipment indefinitely. If no habitable planet exists, the mission transforms into an exercise in space colonization, building rotating habitats or underground settlements on airless worlds using local resources. The resource requirements for any plausible interstellar mission dwarf anything humanity has accomplished. Even a modest generation ship would likely mass hundreds of thousands of tons, requiring either construction in space using materials mined from asteroids or an unprecedented launch campaign from Earth. The energy needed to accelerate such a mass to even a few % of light speed vastly exceeds current global energy production. And we would need either revolutionary advances in power generation or a willingness to dedicate enormous fractions of solar system resources to a single mission with no guarantee of success. These resource considerations lead to questions about whether interstellar missions make sense as human endeavors at all. The entire rationale for sending biological humans across interstellar distances rests on assumptions that might not survive technological advancement. If the goal is exploration and scientific discovery, robotic probes could accomplish this more efficiently than crewed ships. A probe massing a few tons could accelerate to higher speeds than a massive crewed vessel, arrive sooner, and transmit findings back to Earth. The probe wouldn't need life support, food, or social systems. It could hibernate during the long cruise, unactivate upon arrival, and conduct surveys for decades or centuries without concern for crew survival. Of course, robotic probes face their own challenges, particularly regarding autonomy and artificial intelligence. A probe at Alpha Centauri would be over 4 light-years from Earth, making real-time control impossible. Commands from Earth would take 4 years to arrive, and responses would take another 4 years to return. The probe would need to make decisions independently, identifying interesting targets, navigating hazards, and adapting to unexpected situations without human guidance. This requires artificial intelligence far more sophisticated than current autonomous systems, capable of genuine problem-solving and scientific judgment rather than just following predetermined routines. The communication delay also means that discoveries made by an interstellar probe wouldn't benefit humanity for years after they occur. A probe arriving at Alpha Centauri might discover habitable planets, technological artifacts, or revolutionary physics, but Earth wouldn't learn about these findings until the signal arrived over 4 years later. This delay fundamentally alters the nature of interstellar exploration compared to historical precedents. When European ships explored Earth's oceans, they could return with cargo, specimens, and knowledge within months or years. An interstellar probe can only return information, and that information arrives years after the fact, unable to influence the probe's ongoing activities. Some proposals attempt to address these issues by sending not single probes but swarms of small spacecraft. And rather than building one massive vehicle, you might launch thousands or millions of tiny probes, each massing just grams or kilograms. These miniature spacecraft would use laser propulsion with massive Earth-based laser arrays, pushing light sails to high velocities. Individual probes would be cheap enough that losing many to collisions or failures wouldn't compromise the mission. Those that survive would conduct limited observations and transmit data back to Earth. The breakthrough Starshot initiative represents the most developed version of this concept. The project envisions launching gram-scale probes with light sails toward Alpha Centauri, accelerated by ground-based lasers to perhaps 20% of light speed. At such velocities, the probes would reach Alpha Centauri in roughly 20 years. And with data arriving back at Earth after another 4 years, the probes would be too small to carry conventional computers or instruments, instead relying on miniaturized electronics and simple sensors to capture basic images and measurements during their brief flyby of the system. Even this minimalist approach faces substantial technical hurdles. The laser array needed to accelerate the light sails would need to be enormous, perhaps kilometers across, generating gigawatts or more of power. The light sail itself would need to be incredibly thin and lightweight, while remaining strong enough to withstand acceleration and resistant enough to survive impacts with interstellar dust and gas at relativistic speeds. At 20% of light speed, even collisions with individual atoms would release significant energy, potentially damaging the delicate spacecraft. The sail and probe would need some form of shielding, adding mass and complexity to a design that depends on extreme miniaturization. Communicating with gram-scale probes across 4 light-years presents another challenge. The probe's transmitter would necessarily be weak, and its tiny antenna would produce a diffuse signal that spreads over vast distances. Earth-based receivers would need extraordinary sensitivity to detect these faint signals against the background noise of the galaxy. The data rate would be minimal, meaning the probe could transmit only limited information despite traveling across light-years to gather it. You might receive a handful of images and basic measurements, but detailed spectroscopy, extended observations, or comprehensive surveys would remain beyond reach. These limitations illustrate a fundamental tension in interstellar mission design. Larger, more capable spacecraft can carry better instruments, more robust systems, and redundant components, but their mass makes them harder to accelerate and slower to reach their destinations. Smaller, lighter probes can reach higher velocities and arrive sooner, but their limited capabilities constrain what they can accomplish. There's no obvious sweet spot where capability and speed both optimize simultaneously. Every design choice involves trading one desirable quality for another, with no clear winner among the options. The economics of interstellar missions add another layer of difficulty. Even the most optimistic cost projections for something like breakthrough Starshot run into billions of dollars for the laser facility, the probe swarms, and the receiving infrastructure. More ambitious concepts involving larger probes or crewed missions would cost trillions, representing a significant fraction of global economic output. These investments would need to occur decades before any results arrive, and those results might amount to a few grainy images of distant planets or confirmation that the target system contains nothing unexpected. Democratic societies struggle to maintain funding for projects with such distant payoffs. Space agencies routinely face budget pressures for missions lasting years or decades. Politicians and voters question whether missions to Pluto or Mars justify their costs when results arrive only after election cycles have passed. As an interstellar mission requiring centuries of investment before returning data would face vastly greater political challenges. Even if one generation commits to such a project, subsequent generations might redirect resources to more immediate concerns, allowing the infrastructure to decay or canceling the mission outright. This political and economic reality has led some observers to suggest that interstellar missions might only become feasible when undertaken by artificial intelligence rather than biological humans. A sufficiently advanced AI might maintain focus across centuries, managing the technical and logistical challenges without needing democratic buy-in or generational continuity. Such an AI could oversee construction of interstellar infrastructure, launch and guide missions, and process the data when it arrives decades later. The AI wouldn't experience boredom during the wait or lose interest when initial enthusiasm fades. Of course, this assumes we'll develop artificial intelligence sophisticated enough to manage such complex, long-duration projects autonomously. Current AI systems, despite recent advances, remain narrow in their capabilities. They excel at specific tasks but lack general intelligence, common sense reasoning, or genuine understanding. An AI capable of independently managing an interstellar mission would need to match or exceed human-level general intelligence, make value judgments about scientific priorities, and adapt to unforeseen challenges across decades or centuries. Whether such AI is possible remains hotly debated, and even if possible, whether it would maintain interest in human-centric goals like interstellar exploration seems uncertain. The discussion of AI-managed interstellar missions leads naturally to questions about the purpose of space exploration. If artificial intelligence conducts the missions and processes the results, what role do humans play? The traditional justification for space exploration has involved human curiosity, the expansion of human knowledge, and the eventual spread of human civilization beyond Earth. If AI surpasses human capabilities, these justifications become less clear. An advanced AI might explore the galaxy for its own purposes, which might not align with human interests or even be comprehensible to biological minds. This connects to broader questions about the ultimate fate of intelligence in the universe. But if interstellar travel remains impractical for biological organisms due to the vast distances and timescales involved, perhaps intelligence naturally transitions to substrate-independent forms better suited to cosmic exploration. Rather than sending fragile biological bodies across light years, civilizations might transfer their intelligence to more durable forms, whether uploaded minds in computer substrates, nanotech clouds, or forms we haven't conceived. Such beings might find interstellar travel less daunting, being able to hibernate for centuries, repair themselves from radiation damage, or even transmit themselves as information and reconstruct at the destination. These speculations venture far beyond established physics and engineering into what amounts to futurism or philosophy. We don't know whether consciousness can exist in non-biological substrates, whether intelligence can remain stable across centuries of isolation, or whether the experience of such uploaded or artificial minds would retain anything recognizable as human. Yet the combination of interstellar distances and biological limitations seems to push towards such conclusions if we assume interstellar travel will occur at all. The alternative is accepting that intelligence might be fundamentally local, confined to individual star systems by the sheer difficulty of crossing the gulfs between stars. This possibility receives less attention in popular discussions of space exploration, but deserves serious consideration. Perhaps the galaxy contains billions of intelligent civilizations, each confined to its home system, and unable to visit one another despite knowing that others exist. Communication might occur via radio or laser, allowing the exchange of information across light years, but physical travel might remain forever impractical. Civilizations would share knowledge, culture, and science across the cosmic network, but never meet face-to-face or visit one another's worlds. Such a scenario would resolve some puzzles in the search for extraterrestrial intelligence. If civilizations can't travel between stars, we wouldn't expect to find alien artifacts or visitors in our solar system, and we wouldn't need to explain why the galaxy hasn't been colonized despite its age. The galaxy could be full of civilizations, all talking but none traveling, creating a vast community connected by information rather than physical presence. And Earth's absence of alien visitors wouldn't indicate we're alone, but simply that crossing interstellar space is as difficult for others as it is for us. The physics that makes interstellar travel so difficult is universal and unchanging. Aliens facing the same speed of light limit, the same energy requirements, and the same vast distances would encounter identical obstacles. They might develop more sophisticated technology than ours, achieve higher efficiency in their propulsion systems, or build larger and more capable spacecraft. But they can't change the fundamental constraints. Even a civilization millions of years older than ours, with technology we'd consider magical, still faces the problem that Alpha Centauri lies 4 light years away and nothing with mass can reach light speed. As this universality of physical law provides a kind of cosmic equality. The newest spacefaring civilization and the oldest face the same basic challenges, play by the same rules, and operate within the same limitations. Advanced civilizations might have better tools and more resources, but they can't simply engineer around the speed of light or the energy requirements for relativistic travel. In this sense, the problems we face when contemplating interstellar missions aren't problems of insufficient development, but fundamental features of the universe itself. The question then becomes whether these features are absolute barriers or merely extreme challenges. History provides examples of both. Human flight seemed impossible until the Wright brothers demonstrated otherwise. And many predicted barriers to aviation fell as technology advanced. Yet other limitations have proven absolute. We've never found a way to create perpetual motion machines because they violate thermodynamics, and no amount of engineering cleverness can circumvent fundamental physical laws. Interstellar travel might fall into either category. It might be like early human flight, seeming impossible until the right breakthrough occurs. Or it might be like perpetual motion, forever barred by unchangeable physical reality. Most physicists and engineers working on propulsion systems take a middle position. They acknowledge that interstellar travel appears possible within known physics, but recognize that achieving it would require technological advances far beyond current capabilities. And we know that objects can move at substantial fractions of light speed because we observe cosmic rays and other natural phenomena doing so. We know that nuclear reactions release enough energy to power such travel because we can calculate the energy output. We know that materials strong enough to withstand the stresses exist in principle because physics allows them. Yet knowing something is possible in principle differs enormously from being able to actually do it. The gap between theoretical possibility and practical implementation has characterized many technological dreams. Nuclear fusion power has been 30 years away for over 60 years now, not because fusion is impossible, we know it works in stars and hydrogen bombs, but because controlling it for continuous power generation proves extraordinarily difficult. Room temperature superconductors would revolutionize technology, and physics doesn't forbid them, but discovering materials with these properties has proven elusive despite decades of research. Similarly, interstellar propulsion might remain theoretically possible while practically unreachable for centuries or longer. This lengthy timeline for development creates strategic questions about how to approach interstellar propulsion research. Should we invest heavily in developing technologies like fusion drives or antimatter production now, despite knowing they are decades or centuries from practicality? Or should we focus on nearer-term goals, developing infrastructure in our solar system and advancing fundamental science, trusting that the knowledge gained will eventually enable interstellar missions? And the resources available for space exploration are finite, and allocating them to extremely long-term projects means not spending them on other priorities. Some argue that working toward interstellar capabilities, even if success lies far in the future, provides valuable direction for technological development. The goal of reaching other stars drives research in propulsion, materials science, energy generation, and artificial intelligence. These advances benefit other applications, even if interstellar missions don't materialize soon. Fusion power research aimed at spacecraft propulsion might yield fusion reactors for terrestrial use. Materials developed for relativistic travel might find applications in ordinary spacecraft or Earth-based infrastructure. The goal serves as a North Star, organizing research efforts and providing motivation even if the destination remains distant. Others counter that we should solve nearer problems first, establishing sustainable presence beyond Earth before worrying about interstellar missions. Humanity hasn't yet demonstrated ability to maintain permanent settlements even on the Moon or Mars, much less build generation ships or antimatter factories. Perhaps we should walk before attempting to run, developing robust space infrastructure in our solar system and learning to live off Earth before contemplating journeys to other stars. The asteroid belt contains resources that could support billions of people. The outer solar system offers energy, water, and materials for massive space habitats. And we might spend centuries or millennia developing our home system before turning attention outward. This tension between near-term and far-term goals reflects different visions of humanity's future in space. One vision sees steady outward expansion, from Earth to orbit, to Moon, to Mars, to asteroid belt, to outer planets, to interstellar space, each step building on the previous one. Another envisions long periods of consolidation within one region, followed by leaps to new frontiers when technology permits. History provides examples of both patterns. Polynesian expansion across the Pacific occurred gradually, island by island, over thousands of years. Yet European exploration crossed the Atlantic suddenly once sailing technology matured, without requiring incremental island settlements in between. For interstellar travel, the distinction matters because the technologies required might not develop naturally from solar system colonization. The propulsion systems needed to move between planets differ fundamentally from those needed for interstellar journeys. Chemical rockets work adequately for traveling within the solar system, and ion drives can slowly ferry cargo between planets. Yet neither approach scales to interstellar distances. Fusion drives, antimatter engines, or laser propulsion represent discontinuous leaps rather than incremental improvements. Mastering them might require dedicated research programs rather than emerging naturally from ongoing spaceflight operations. And the same applies to other technologies needed for interstellar missions. Life support systems for Mars missions last months or years, but generation ships need systems lasting centuries. Manufacturing and repair capabilities for asteroid mining operations might not scale to the self-sufficiency required for isolated interstellar vessels. Navigation and communication across solar system distances differ enormously from managing starships light years from home. Each domain might require specific research and development that won't occur automatically as byproducts of inner solar system activities. Recognizing these gaps has led to occasional proposals for dedicated interstellar research programs. The 100-Year Starship Initiative, sponsored by DARPA and NASA, aimed to foster research and planning for interstellar missions expected to launch in a century. The project emphasized that its goal wasn't to build a starship immediately, but to ensure that the necessary research occurs and that institutions capable of maintaining century-long projects exist when needed. The initiative explored propulsion, life support, social organization, and mission architecture, producing studies and workshops rather than hardware. Such programs face criticism for their speculative nature and distant timescales. Skeptics question whether planning for missions a century away makes sense when our understanding of technology and society will change dramatically in that time. The world of 1920 couldn't have meaningfully planned space missions for 2020. The technology, politics, and social context changed too radically. Similarly, detailed planning today for 2,120 Starship launches might produce documents that future generations find quaint and irrelevant, based on assumptions that didn't survive or ignoring developments we can't foresee. Proponents respond that some aspects of interstellar missions remain relatively insensitive to specific technological details. The distances won't change, the speed of light limit won't change, and the basic energy requirements won't change. Whatever propulsion system eventually enables interstellar travel will need to address these fundamental constraints. Research into basic physics, material science, and energy generation remains valuable regardless of exactly how future missions are implemented. If nothing else, attempting to envision interstellar missions highlights gaps in current knowledge and suggests productive research directions. The philosophical and cultural aspects of interstellar exploration also warrant consideration independent of specific technologies. Questions about why we might go, what we hope to find, how to organize multi-generational missions, and what role humanity plays in a universe of vast distances don't depend entirely on propulsion systems. Thinking through these issues now, while we're not committed to particular approaches, might prove valuable when actual missions become feasible. Cultures evolve slowly in some respects, and values that take generations to develop might need that long lead time. This brings us back to the fundamental question of why interstellar travel matters. And if it's extraordinarily difficult, resource-intensive, and unlikely to occur soon, why think about it at all? One answer is simply that humans are curious about what lies beyond our cosmic neighborhood. We wonder whether planets orbiting other stars harbor life, what forms that life might take, and whether intelligence exists elsewhere. These questions spark imagination and drive scientific inquiry regardless of practical considerations. We want to know, even if knowing requires extraordinary effort. Another answer points to long-term survival. Concentrating humanity and its descendants on a single planet or even within a single star system creates existential risk. Cosmic accidents, stellar evolution, or catastrophes of our own making could end Earth-based civilization. Spreading beyond our solar system would ensure that some branch of humanity survives, even if disaster strikes our home. This motivation doesn't require fast interstellar travel or missions within current lifetimes. Even slow expansion over millions of years would eventually distribute humanity widely enough to ensure survival. A third motivation emphasizes the journey itself rather than destinations. The process of developing interstellar capabilities drives scientific and technological advancement. The challenges force us to think carefully about physics, engineering, biology, and social organization. Solutions to these problems might benefit humanity even if we never launch starships. This argument treats interstellar travel as a goal that organizes effort rather than a destination we expect to reach soon. Similar to how moonshot goals can focus research even if the specific objective seems less important than the progress made toward it. These varied motivations lead to different conclusions about priorities and timelines. If the goal is answering scientific questions about nearby stars and exoplanets, robotic probes make more sense than crewed missions, and incremental progress towards small, fast spacecraft seems appropriate. If long-term survival drives the effort, timescales of centuries or millennia become acceptable, and generation ships or even slower approaches might suffice. If the value lies in driving technological development, ambitious goals with uncertain feasibility might serve better than conservative, achievable plans. And the current state of interstellar propulsion research reflects this mixture of motivations and approaches. Some groups work on near-term technologies like solar sails and laser propulsion, aiming for small demonstration missions within decades. Others investigate fusion propulsion, accepting that practical systems lie much further in the future, but believing the research valuable. Still others explore even more speculative concepts like antimatter rockets or warp drives, working at the boundaries of known physics. No consensus exists about which approach deserves priority, and funding remains modest across all areas. This diversity of effort might actually be productive. Given the uncertainties involved, exploring multiple approaches in parallel makes sense. And we don't know which technologies will mature first or which will prove most practical for actual missions. We don't know whether breakthrough discoveries will enable capabilities currently considered impossible or whether fundamental limits will prove more restrictive than hoped. Maintaining research across various propulsion concepts keeps options open while advancing understanding in multiple domains. The same logic applies to mission architectures. Rather than committing now to generation ships, sleeper ships, or robotic probes, we might benefit from developing the technological and social foundations that would support any of these approaches. Advances in life support, artificial intelligence, materials science, energy generation, and social organization enable multiple pathways to interstellar travel. Building this foundational capability provides flexibility, allowing future generations to choose approaches based on circumstances we can't predict. This strategy of building capability rather than committing to specific missions resembles how we've approached other complex challenges. We didn't decide in advance exactly how computers would be used before developing them, and we didn't know precisely how the internet would reshape society before building it. Instead, we created enabling technologies and let applications emerge. The same approach might work for interstellar travel. Develop the underlying capabilities and let the specific implementation depend on knowledge and circumstances that will become clear later. Of course, this assumes that building those capabilities serves other purposes beyond interstellar missions. And if fusion power, advanced AI, or self-replicating manufacturing only matter for starships, the argument for developing them weakens. But most of these technologies offer benefits across many domains. Fusion power could transform Earth's energy infrastructure. Advanced AI promises applications in medicine, science, and industry. Self-replicating systems might enable space manufacturing and solar system development. Building these capabilities serves immediate interests while incidentally advancing interstellar prospects. The question of timescale remains central to any discussion of interstellar travel. When might humanity actually send missions to other stars? Predictions vary wildly, from optimists suggesting robotic probes within this century to skeptics doubting it will happen for millennia if ever. And the uncertainty stems partly from technological unpredictability. We can't know when key breakthroughs will occur, and partly from questions about social priorities and resources. Will future generations consider interstellar missions worth the enormous investment required? Historical analogies provide limited guidance. Space exploration enthusiasts often compare interstellar missions to Columbus crossing the Atlantic or Magellan circumnavigating the globe. These comparisons suggest that what seems impossible becomes routine once someone demonstrates feasibility. But the analogy breaks down under examination. Columbus's voyage took months, not centuries. The ships used existing technology rather than requiring revolutionary advances. The resources needed represented a tiny fraction of national wealth. The risks, while real, it affected dozens of people rather than thousands. And the benefits became apparent quickly, shaping geopolitics within years. Interstellar missions share none of these characteristics. They require technology that doesn't exist, timescales that exceed civilizational continuity, resources that dwarf historical expeditions, and benefits that might not materialize for centuries after investment. A better historical analogy might be massive infrastructure projects like the Great Wall of China or the cathedrals of medieval Europe, projects spanning generations and consuming substantial resources for goals that combined practical benefit with symbolic or cultural meaning. Yet even these projects were undertaken within single civilizations with continuous traditions, not handed across multiple generations that might reject their predecessors' priorities. This points to perhaps the deepest challenge facing interstellar missions: maintaining cultural and institutional continuity across the timescales required. A civilization needs to remain stable and committed for decades at minimum, probably centuries, to develop and launch interstellar missions. The institutions managing the project need to survive political changes, economic fluctuations, and shifting cultural priorities. The knowledge base needs to be preserved and transmitted across generations of researchers and engineers. The motivation needs to survive long enough for the project to reach fruition. Human history offers few examples of such continuity. Religions persist across millennia, but even they experience schisms, reformations, and doctrinal drift. Political systems typically last centuries at most before revolution or collapse. Scientific institutions have only existed for a few hundred years. Corporations rarely survive more than a century or two. The idea that we could create organizations or social structures stable enough to manage interstellar missions across the required timescales seems optimistic given this track record. Yet perhaps this simply means that interstellar missions require different social technologies, institutions designed for multi-generational or multi-century operations. These might look different from current organizations, incorporating redundancy, distributed decision-making, and mechanisms for preserving knowledge and purpose across time. As science fiction often depicts space agencies or private foundations that persist across centuries, but creating such institutions in reality would require innovations in governance and social organization as significant as the technological advances needed for propulsion. The alternative is that interstellar missions might only become feasible when implemented by entities that don't face these temporal constraints. Artificial intelligence, if sufficiently advanced, could potentially maintain focus across centuries without the generational discontinuities that plague human organizations. Uploaded human minds might retain interest and commitment across timescales that biological humans can't sustain. These possibilities remain speculative, but they suggest that the question of when interstellar travel becomes possible might depend as much on developments in intelligence and consciousness as on advances in physics and engineering. In the end, the vast distances to Alpha Centauri and beyond represent more than just an engineering challenge. They force us to confront fundamental questions about what intelligence can accomplish, how civilizations maintain purpose across time, and whether the universe ultimately allows for the kind of cosmic expansion that features so prominently in our science fiction. The gap between our current propulsion technology and what would be needed to reach even the nearest stars within human lifetimes isn't just a matter of better rockets or more powerful engines. It reflects deep constraints imposed by physical law. They're constraints that might or might not have solutions compatible with biological life and human-scale civilization. We've made remarkable progress since the first satellites and moon landings, developing capabilities that would have seemed magical to earlier generations. Yet the distances to other stars remain stubbornly, vastly greater than anything we've crossed. 4 light years to Alpha Centauri might as well be 4 million given current technology, and even our most ambitious theoretical propulsion systems would require revolutionary advances to cross that gulf in reasonable time. Whether those advances will occur, whether they are possible at all within the laws of physics, and whether humanity will still exist and care about such journeys when they become feasible, remains unknown. What we can say is that the challenge is genuine. The obstacles are formidable, and the solutions will require either patience measured in centuries or breakthroughs that reshape our understanding of what's possible. The stars beckon, as they always have, but they remain extraordinarily far away. Our current engines can barely lift us beyond Earth's gravity well, and the engines we can imagine might someday carry us to nearby stars, but only with effort and resources that dwarf anything yet attempted. Whether that effort will be made and what form it will take depends on choices that haven't yet been made by civilizations we can barely envision. For now, we watch the stars, we calculate the distances, we study the physics, and we wonder whether the gap between here and there will someday shrink from impossible to merely extremely difficult.